Hi guys, welcome back to our HYSYS videos. Today we want to talk about making the reactors diabatic, which means that there's heat transfer from this reactor. Why are we doing that? Well, there are two reasons basically. One is that diabatic reactors can help increase yields because in this case, methanol reactions are exothermic, so you tend to have a higher yield at low temperature. So you kind of want to cool the reactor down. And secondly, of course, you want to have diabatic reactors because you want to generate steam. Okay? So, yeah, let's try it on this reactor. And now this yield is kind of small, actually. Yeah, I also want to increase it a bit. So, want to increase it to about 10,000 or no 5,000 kg moles per hour, because that is a typical factory production. So of course, when I do that, the pressure drop increases. So I kind of have to make the reactor a little wider. And to do that, what I simply do is to decrease the length. So I decrease it to 20 meters, and now the pressure drop is within something reasonable. That is about 32. Let's put it 18. And 18 is about 50 kilopascals, and that is, to me, pretty acceptable. Yeah, and the diameter is about 0.6 meters. So if I just put it at 15, it'll be like 0.6515. Let's put it at 10. I mean, that's a pretty reasonably sized reactor. Okay, 10 kilopascals. Wow, that's good. 10 kilopascal pressure drop across the whole thing. So let's put it at about 8. I think 8 or 7. So I'll just have a 7 meters long and about 1 meter wide. That's an L by D ratio of about 7, a little over 7. So that's pretty reasonable. And what we see is that our pressure drop is insanely low, and that is good news. And we are producing a lot more methanol. So now we have upped our methanol production to about 5,000 kilograms per hour. That's good news. Okay, so basically, what else? Yeah, we want to make the reactor diabatic. So how do we do it in a more correct way? Okay, first of all, you need an energy stream. So we want to be generating high pressure steam. So I put high pressure steam generation energy in this case. I'll just press enter. And you'll notice that the plug flow reactor has turned yellow because you don't solve anything. So you have an unknown duty. So all you have to do is to specify the duty. So let's just put like 100 over here. And you see the reactor has cooled down insignificantly. Okay, if not, you can put about 5,000, and that will be okay as well. Maybe 100,000 or 10,000, and 1E5, and you get the idea that you can just specify your own heat generation rate. So about 1E8. Okay, that's maybe too much. I think I cooled it down too much. Okay, so now that is something reasonable, about 1 times 10 to the 7th, so that the reactor doesn't cool down too much. In fact, it's slightly isothermal now, and that's cool and all, to try and get an isothermal reactor, because you see the outlets at about 270, and we have a pressure drop of about 4 kilopascals. Heat flow is about 2778 kilowatts out. But then, hey, Theo, what about the, how do we actually calculate the heat flow in HYSYS? Well, that's good news for you. You can actually use a formula to calculate the correct amount of duty. And using HYSYS, there's this formula calculation. The duty out is about 160 kilowatts. Now, how did that come about? Well, HYSYS actually gives you some kind of method of calculation. Well, basically, you see they treat the plug flow reactor like some sort of heat exchanger, which is correct because these reactants are going in at a pretty hot temperature, and you want to be generating some steam, so you want to be boiling some water, and by doing so there's some sort of heat transfer between a hot and cold fluid, and based on the temperatures of the hot and cold fluid we can calculate some sort of heat transfer coefficients. As you can see here, heat medium side heat transfer inflow, and tube side heat transfer inflow. So the tube side is inside the plug flow reactor. So this plug flow reactor is one big tube, and because we have one big tube, well, there is some area, but if you want to increase the area, you have multiple tubes in parallel. So if you want to do that, you come here, you go to the rating tab, and you look at the number of tubes. At present, it's at 20. And if you want to increase it to maybe 100, you can do so in the following manner. Now, by doing so, your pressure drop kind of increases a little bit, and your cost will of course increase, but the thing is that your heat transfer is a lot better. See, it's 314, that's almost double of the last time, because you effectively, increase your area quite a fair bit. So that's how you kind of get your get HYSYS to automatically calculate it for you. And now let's go into the more nitty-gritty details. Yep. So this is all we have discussed before. The number of segments, yes, we have discussed before. Well, let's go into the heat transfer side. So the heat medium side transfer info, you'll see this wall heat transfer coefficient, this molar flow. You'll see some heat capacity here. You'll see some inlet temperature here. And that's it. So what are you using? What is this side talking about? Well, this side is basically the coolant jacket that you're using to cool the plug flow reactor. And what you basically want to do is to kind of match all these parameters to ensure you are actually using water. Water vaporization. So basically we are using it to generate steam, and so this wall heat transfer coefficient should be representative of that steam generation. So what do? You see now that it's 2.6626 E plus 1 kilojoule per hour per meter square per degrees Celsius. So how do we look at something that's appropriate for water? Well, if you just do a quick search online, going to Engineer's Age, don't worry, I can put this in the description, and it says typical values of heat transfer coefficient, and I'm looking specifically at forced convection, and you have boiling water in a pipe, which is quite close to what we want, because we want boiling water at high pressure to generate high pressure steam. So we are taking condensed water at high pressure and we are vaporizing all of it so that we can generate high pressure steam for the plant, and at the same time cool down the plug flow reactor. So the heat transfer coefficient is about 50,000 watts per meter square per Kelvin. So let's try and key that into HYSYS. So that's 50,000. Then you have to select watts per meter square per Kelvin, or equivalently watts per meter square per degree Celsius, and you just click that. You have a 1.8 E to the 5, and that will give you this. And guess what? You see your power flow has gone up to be about 1 megawatt, which is pretty high. Yep, 1 megawatt, 1.1069 kilowatts. And you got to kind of specify your molar flows, heat capacity, and inlet temperature as well. So for one, we know high pressure steam is going to be generated at around 250 to 254 degrees C. I'll just use a median temperature, about 253 degrees C. You can see that where your temperature difference starts to decrease, the power out, the heat transfer, the amount of heat transfer out actually decreases also. And of course, you want the heat capacity to be something representative of water vaporizing. So what do? We take note of two facts. One is that when there's a phase change, there's hardly any, any kind of temperature change. So I'm going to just make sure this is a very large number. This heat capacity is a very large number. Now, how large? Well, you'll need to do some simple calculations first. Okay, let me delete that. That was unintended. So basically, I want to find out some latent heat of vaporization of steam. So what I'm going to do is I'm going to do a simple heater here. So it's something, I just call this a high pressure steam generator, because this plug flow reactor is giving out an energy stream, and I want to calculate how much steam I can actually produce. So I'm going to connect this here by doing the control trick. I'm going to save it, and I'm going to drag a stream out. So in this, I've made two new streams, material stream 2 and 1, using the same control. So what I was doing is that, okay, if you missed it, I'm just pressing control, I'll pull it out, and I'm going to let go, and a new stream is made. So inside here, you will have a condensed, stream, condensed high pressure steam, which is just condensed high pressure water, and I'm going to make pressure around 4250 kilopascals. And the fluid package I use is the ASME steam tables, which is kind of obvious. You have to use steam tables for this. And I'm going to just use water here. I'm going to press OK. And the vapor phase fraction is going to be 0. So it's effectively going to be saturated steam. I mean saturated condensed water. Well, you can subcool it if you want, and I suggest subcooling it because there will be some temperature change along the way. So I'm just going to put it at 250. So it's going to come in at 250. Okay, yeah. So the reason why you subcool it is because there are pressure drops across every heat exchanger you go through. And with every pressure drop, there's going to be a slight pressure change. And with every slight pressure change, the temperature is going to shift down slightly. So you kind of have to allocate for that. So my initial guess is that water is going to come back at 250 degrees C. You can change it later on. I'm just going to initial guess it at 250 degrees C. So that's 250 degrees C in, and I'm going to put a so I'm going to do the outlet stream, so generated HPS out, and it's going to be one phase vapor phase fraction. I'm going to put all of it's vapor, saturated vapor, and I'm going to close. I was closing this generated HPS. I'm going to the HPS generator. I'm going to put a delta P, a pressure drop of about 100 kilopascals. Okay, which is quite reasonable for condensing a unit. Sometimes it's 80. So basically, we have a pressure drop and we have steam being generated from this unit. And yeah, so now we have this steam that's being generated. This is just an initial guess. What we actually need to look for is this thing called, I think, what is that? Heat of vaporization. So it's in kg per kg mole here. Can you see? So heat of vaporization kg per kg mole, and it's in 3.053 e to the 4. So per kg mole, I will have 3.053, the heat of vaporization. All right. So I'm going to put that number in here. 3.053 E4. In fact, you can make it slightly larger. And the molar flow, I'm going to liken it to this molar flow here, which is 86.12. And I want to see whether it kind of matches. So yeah, we have 743 kilowatts out, and yeah, that's basically it for the heat medium side transfer. This is the what do you call that? The cooling water side, so called. So the coolant, which is condensed HPS or high pressure water at about 250 degrees C, it'll be coming in at about 86.67. So we'll just have to kind of iterate it until these two numbers actually match pretty closely. 86.5. So if 86.5, here's 86.8. So I'll put 86.75. So I'm trying to get this number here, this molar flow rate. Now it's 86.03. And this should match pretty closely. So 86.4. I want to see whether it... that's better. So now the outside one's 86.81. So let's put 86.45. Let's see whether it matches. So this mole flow should match the mole flow here pretty closely. And okay, I'm just going to leave it as that. So I'm going to save this file. Okay, and that my friend has helped us to get the amount of steam we can actually generate. Okay, so what is next? We actually have to do the tube side transfer info as well. So here we can see HYSYS is actually using some kind of Nusselt number correlation. So don't worry, there are a few we can use, and basically what I got from this website is clarkson.edu. It's over here, and there's a very long description of what the Reynolds number and Nusselt number should be. But I'm just going to use a simple correlation. It may or may not be correct. So it's this Nusselt number equals 0.023 times the Reynolds number to the power of 0.8 and Prandtl number to 1/3. So let's just key these things in to HYSYS. So these are the defaults by HYSYS. I mean, if you don't know what to use, you can use these defaults first. Okay, so yeah. So 0.023, so I'm going to put 0.023 here. And the B will be the power of the Reynolds number, which is 0.8, as we saw previously. And the C will be the power of the Prandtl number. So I'm going to put 1/3 with all 0.33333. Okay. So that basically helps us to get the correct heat transfer coefficient based on the shell side, which is the shell side, which is basically where the steam is being generated, and the tube side. So again, based on these heat transfer coefficients, we got to check how much. As you can see that once we key in our Nusselt number correlations, we see that our HPS actually drops down to about 67.16 kgmol. So let's change. We got to iterate until this is pretty close, 67. Yeah, we got to iterate until these two numbers closely match. And in this case, we have, so it's about 574.6 kilowatts out. And that actually helps us to, get a good sensing of how much heat can be transferred out. Now, if you want to bring this down, we should, we should try and bring this down to 280. But never mind, we can talk about that later. Okay, so what I've basically shown you today is basically how to turn your reactor from an adiabatic reactor to a diabatic reactor that generates high pressure steam in a proper manner. And how do we do that? We've actually used this, we actually make an energy stream, and we have used the formula, this formula which uses some Nusselt number correlation to actually tell us how much duty this plug flow reactor can actually, how much heat it can actually transfer out. I mean, based on, let's say, yeah, based on the, what is that? I might try to say, yeah, based on how much area. Of course, you have the heat transfer, heat exchanger, classic formula, which is Q equals UA times L log mean temperature difference. So HYSYS will kind of like calculate the area A based on how many number of tubes. So I have to go to the design. Oh, sorry. Yeah. So it goes to the rating. You have to see how many number of tubes, and based on that, it'll calculate some kind of heat transfer area. So that fixes A. Then U is calculated based on what you have input here, which is all these heat transfer coefficients, the heat capacity, blah blah blah, and of course the Nusselt number as well. So all this actually factors into the U, because this is the convection heat transfer coefficient. It helps to calculate that on the reactor side, and then of course on the coolant side you have this wall heat transfer coefficient, etc, etc. So now you have to properly turn it into a diabatic reactor. And of course you can actually see the temperature profile along the whole reactor. You see it starts at 277.7 and shoots up to 291, then it drops back down to 288. And yeah, that's basically it for this video. I don't want to go on yapping too long. It's already been 20 minutes, so yeah, that's all I have for you. Thanks for watching. I'll see you again. Bye bye.